Bingo, 1 o'clock rock here on Think Tech, talking about research in Manoa, my favorite show. And we have our special guest, Dr. Bin Chen, PhD, Hawaii Institute of Geophysics and Planetology, School of Ocean and Earth Science and Technology, that's SOWEST, at the UH Manoa. And today we're going to talk about the core. I mean, it's the core of the Earth, doesn't it?
Yes.
Mineral physics journey, this is like Jules Verne, mineral physics journey to the center of the Earth. Welcome to the show, Bin.
Yeah, aloha, Jay. I'm very glad to be here to present our research at the University of Hawaii.
That's great.
About the core.
About the core, yeah. We need to know more about the core. That kind of rhymes, doesn't it?
Yeah, definitely, yeah.
So tell us what you do as a researcher at the HIGP in the SOWEST.
Yeah, I'm a mineral physicist. So in our laboratory, we simulate the conditions found in the interior of the Earth and other planets. And then we probe the material properties under these conditions, trying to understand the compositional makeup of our Earth and other planets.
Okay, but we are agreed, are we not, that what's on the periodic table of elements is the extent of it. In other words, you're not going to find anything in the core that is not on the periodic table of elements.
Yes.
Okay.
Yeah, absolutely. I think one of our pioneers in our research field. So he has one sentence about the composition of the core. So basically, every element in the periodic table of elements can be in the core.
Really? Oh, that is something.
Yeah.
So not only is it limited to the periodic table, it's got everything from the periodic table.
Yeah, but it's all like in terms of what are the concentrations of this element in the core.
So when you say core, how far down do I have to drill? You know, when I was a kid, you're going to enjoy this. When I was a kid, they would say, start digging here in this lot, start digging. And if you dig long enough and hard enough, you will come up in China.
Yeah.
Did they say that in China?
True. Yes.
If you dig hard enough and long enough, you'll come back to the New York.
Yeah, definitely. This might be a shortcut.
So what is the core? I mean, how far down do you have to go to get to the core?
If we drill hard enough, and then if we drill for many years, and then when we drill 2,900 kilometers from the surface, and then we can reach the core metal boundary, so where the core and the mantle meet at that depth.
What's the difference between the core and the mantle? Is the mantle? Oh, the mantle is the skin of the core.
Yeah.
You penetrate the mantle and you're in the core.
Yeah. Then you can reach the core, and then you can see some hot irons in the Earth's liquid outer core.
Yeah. Is it all hot in there? Everything in the core is hot.
It's very hot.
Yeah.
The temperature could be 3,000 degree
Fahrenheit.
Degree Celsius.
Oh, Celsius. Whoa,
Yes.
that's really hot. And does it get hotter as you get to the center?
Yeah, it will get even hotter if you reach the inner core, and then the temperature could be 5,000 Celsius to 7,000 Celsius.
What keeps it so hot?
That is from our daily life. We know that if we drill to the interior of the Earth, when we drill a little bit, so the temperature will rise.
Yeah.
So if you have been to some mines, the temperature will rise. It's partly due to the radioactive element in the interior of the Earth.
Oh.
So this radioactive element will decay, and then it will produce some heat. And also it will also due to the evolution of the Earth, because the Earth was formed from basically dust, and then when it forms, all this gravitational energy will also contribute to the heat of the interior of the Earth.
Gravity itself.
Yeah.
But what about the radioactivity? I mean, what's radioactive in the core? Like uranium?
Uranium, thorium, or potassium.
And
Yeah,
so-
some people believe that there could be a significant amount of potassium, radioactive potassium, in the Earth's core.
That has something to do with weight, doesn't it? I mean, it's something that's radioactive. Radioactive material is always heavier, like heavy water, and uranium is heavy, and
Yeah.
I guess potassium that's radioactive is also heavy.
Yeah, it's radioactive. It's mainly because it's unstable, so it will decompose to some other element,
Yeah.
and then so during this process, it will produce a significant amount of heat. Like the nuclear power plant. So we use the radioactive energy from this element.
But it's also creating radioactivity too. I mean, if you were there, not that you want to be there, but
Yes.
if you were there, you would get heat, but you would also get radioactive. It would kill you two ways immediately.
Yes, definitely. Yeah, you don't want to be there.
You don't want to be
Yeah.
there. But you want to be there. You want to
Yes.
drill down and find out what's there. And you never got to explain to me, but this thing on the table, this is something to do with finding what's in the core. Yeah?
Yes. So this is a device called a diamond emerald cell. So in this diamond emerald cell, we have two opposing diamonds, as you can see through this window. Then we squeeze our tiny samples between these two diamonds. We just squeeze it by turning the screws. And then because pressure, by definition, is the force over an area, right? And then if you decrease the area that the force is applied to, then you can have very high pressure.
So with this, you
Yes.
can have high pressure.
Yes.
And do you need some other tools to turn it really hard, or can you do it with your hands?
We can just use our hand. We can have two wrenches, and then we can turn, and then it can reach the core pressure.
Can you do it now, or
We don't have a wrenches.
You need
but,
a wrench.
Yeah, so it's very easy to increase the pressure. And
so when you increase the pressure and the diamonds come together, what happens?
so we have a metal gasket between the diamond, and we drill a hole in this metal gasket. So our samples will be in this hole. And the metal gasket is to prevent the diamond from contacting with each other.
Okay.
So whenever we have diamond in contact with each other, then the diamond will break.
Oh, so
Yeah.
this preserves the diamonds. You don't want to lose the diamonds.
Yeah.
Diamonds are a researcher's best friend.
Yeah, definitely. Yeah.
So why diamonds? Why do you need diamonds for this?
Because diamond is the hardest substance in the universe we know today. And because it's very hard, so we can squeeze it hard enough to increase the pressure. And also diamond is also transparent. So we can see through see through the diamond, and then we can see our samples. And then we can use some other like a laser spectroscopy or X-ray to probe the material properties under in situ under high pressure.
How much pressure can you achieve with this device?
For this particular device, so the flat surface of the diamond is 150 micron in diameter. So using this device, we can reach 2 million atmosphere pressure.
Oh,
Yeah.
that's pressure.
Yeah, that is the pressure found in the Earth's outer core.
Oh, outer core.
Yeah.
But in the inner core, it's even greater.
In the inner core, though, so we have to reduce the diameter of of the flat surface of the diamond. And if it is 50 micron in diameter, then we can reach 300 gigapascal or 3 million atmosphere pressure.
So if you reduce the size, the diameter of the contact,
Yes.
and you apply the same force, then the force for that size is greater.
Yes.
If you, for example, double the size, then the force is half. And if you half the size, the force is double.
Yes, that's
Something
right.
like that.
Yeah.
Okay. Then you do this in the laboratory. This doesn't go into the center of the Earth or anything.
Yeah, we squeeze a piece of our samples using this device. So when we can simulate the pressure that can be found in the Earth's core, then we can use X-rays or lasers to probe the material properties. And then we can use the knowledge about these material properties to determine what are there in the Earth's core.
Can I look at it?
Yeah, sure.
And I can see, right?
Yeah, you can
I can see into
through
that.
the
I can
window.
see. Well, I can see light on the other side. Yeah.
Yes, that's right.
So in fact, this light is coming in these ports. These are
Yeah.
all open. Oops,
Mhm.
it's heavy, by the way.
Yeah, yeah.
So the light is coming in, and I can see the light if I look down into it.
Yes.
And it has some
And then,
handwriting on it.
So you have to use a microscope to see the samples. So we have samples in this loaded in this cell.
Mhm.
It's a piece of iron carbide samples. So
So-
this is a candidate for the Earth's inner core.
Okay. How do you get the materials that you put in this squeezing device? How do you want to drill down, right? You have to drill down to the mantle and then further into the core. How do you do that?
No, we actually synthesize in our laboratory for these iron carbide samples. So we call this a pocket-sized high-pressure device. So you can actually put it in your pocket, and then you can carry it with you to, for example, Chicago. There's a synchrotron facility called the Advanced Photon Source of the Argonne National Lab. So we can use their high brilliance X-rays for our measurement. And then for these samples that is used in this diamond anvil cell, so we synthesize in our lab using the large volume press or the multi-anvil apparatus. So this is a press that we cannot carry it with us in a pocket.
It's too big.
It's very big. So in our laboratory, so I will show in some of the slides.
Okay.
In our laboratory, we have a 2,000-ton multi-anvil press. So this press is much taller than me. And then we can reach the pressure and the temperature conditions found at the top of the lower mantle.
Is that here?
Yeah, it is in Hawaii.
HIGP and UH Manoa?
Yes, yeah.
Oh, we're gonna see pictures of that.
Yes. Sure.
Okay, I can hardly wait. So we're gonna take a short break, and we come back, we're gonna see some pictures about this press. We're also gonna find out about the conference that's taking place in June. Lots of stuff when we come back here on Research in Manoa with our guest, Dr. Bin Chen of HIGP. We'll be right back, you'll see.
Hi, I'm Ethan Allen, host of Likeable Science on Think Tech Hawaii. Come join us every Friday at 2 p.m. when I interview interesting scientists about what they do, why they do it, and why we should all care about it. It's a lot of fun to see. We hear, and you can learn interesting stuff. You'll hear all kinds of fascinating science, and we know you'll have a great time. Hope to see you then. Bye-bye.
Aloha, namaskar, and hello. My name is Anu Hittel, and I host a show, Climate Change Beyond Outrage. In it, we go beyond outrage to look at solutions to climate problems facing people, nations, and the world. Join me every Tuesday at 1 o'clock Hawaii Standard Time. See you then.
Aloha, my name is Richard Emery, and I host Condo Insider. We talk about issues facing the condo association throughout Hawaii and talk about solutions. When you think about it, about 1/3 of our population lives in some form of common interest real estate. We broadcast every Thursday at 3 p.m. Please tune in and thank you. Aloha.
Okay, bingo, we're back and we're looking at the mineral physics. Mineral physics, the core. It's like a movie, it looks like a movie. Journey to the center of the earth. It is a movie. Is it a movie?
Yeah, it is a movie. So it's a sci-fi movie. So I'm a big fan of sci-fi movies. So I put together this slide trying to show that like our science is cool, right?
It's very cool, except it's hot. It's hot science that's cool.
Yeah. This is but what I'm going to talk about today is not about taking a imaginary vehicle down to the center of the Earth, or we can find a mystery cave that we can go to the center of the Earth. Instead, so I'm going to talk about our high pressure mineral physics research simulating the pressure, temperature conditions found in the interior of the Earth,
Okay.
and trying to understand the Earth's interior better.
Okay, so we'll show your slides and then you can describe them. How's that?
Yeah.
Okay, here's one. What is this telling us?
So this our topic today is about the core. As we can see that all this terrestrial planet, it has an onion-like internal structure. So all of these planet moons, it has a core. The core is considered to be the engine of the planet. It's like the engine of a car, so that is partly the reason that a car can move. And then the core, for example, is the engine of our planet.
The engine is if the core actually causes motion, causes circular motion, the revolution, rotation of the planet. Is that true?
No, the core is, so the convection of the, in the core is the reason that we have a magnetic field.
Ah,
Yeah.
okay.
So that's actually my next slide.
Okay.
So the core was discovered in about 100 years ago. Exactly 100 years ago by Oldham. So at that time, so there were not many seismic stations available, but so he can still determine that the Earth's center should have a dense sphere at the Earth's center. And then 30 years after that, Lehman discovered that the Earth's core might be molten. Part of the Earth's core might be molten. That is from the observation that there is a shear wave shadow zone by seismic studies. Because we know that the shear wave cannot travel through a liquid or melt.
So, no, this kind of research, it's like you can't get to the core and look. That would be bad.
There's no direct sampling of the core.
So you have to use logic.
Yes.
You have to reason it out. And that's how you make discoveries like this.
Yeah.
Okay, what else we got?
I think previous slide, I think there's also some other information I want to show. Because so there's some, a lot of people have found this iron meteorite. So now the question is that what the Earth and planet core is made of. So from this iron meteorite, that people think that the Earth's core might be made of iron nickel. And the convection layer, the convection in the Earth's liquid outcore is the reason why we have a magnetic field. That is also partly the reason why we have the Earth has life.
You agree?
Yes.
Okay.
Yeah. So this, so I introduced a little bit about the device we used in our research. This is the diamond emerald cell. That we can using this diamond emerald cell, we can use so we can generate the pressure conditions from at the center of the Earth. And then in our laboratory, we also have this device called a large volume press. So because it has a large volume, so we cannot reach as high pressure as the diamond emerald cell. So here I have this cartoon. It shows for 98,000 atmosphere pressure. In order to generate this pressure, we need to put an elephant weighted 1 ton on a very small area, like a 1 millimeter square.
So this press is in UH Manoa, as you mentioned.
This is the press available at Argonne National Lab.
Oh,
because
okay.
This press, it's a 1,000 ton press, so it has access to the X-ray. So we lifted this whole press up, and then we can just move this press by micron resolution. So we can move this press to put our sample to the X-ray, and then we can probe the...
Under it. So the whole thing goes on top.
The whole thing is lifted.
Yeah.
Like, and then on a stage.
Yeah.
Then we can move the stage, then to move our samples to the X-ray.
Right, and then...
Then we can probe the X-ray, the material properties of these samples under high pressure and high temperature conditions.
And the weight goes on top of the press. When you want to put that heavy weight on top, it just goes on top of the press. Yeah.
You mean how the pressure is generated in this press?
The weight that you use to generate the pressure. Yeah.
That is by the hydraulic.
I see, by
pumping.
hydraulics.
Yeah. by
So you don't
hydraulic.
have to have lead weights or anything.
No,
That
no,
would be too big anyway.
Yeah, so this is called a 1,000 ton metric ton press. Of course, we cannot put a 1,000 ton metal on this. So we have to rely on the hydraulic compression.
Okay, so
Yeah.
what's the difference between the one we saw and the one you have?
The one we have, I have a picture in one of my
Well,
next
let's see
slide.
that. Yeah, let's see that.
Yeah, this is the press available at the Hawaii Institute of Geophysics and Planetology of University of Hawaii. This is a 2,000-ton multi-anvil apparatus. This is the left one, so the blue press. In this press, there's a second stage compression, two-stage compression. One is we have 6 wedges. It has formed a cavity over a cube, and in this, so we put our samples at the center of these 8 cubes, and we compress the wedges, and then we can generate a high pressure. We can apply pressure to our samples, and then we can also use resistive heating to heat our samples to very high temperature.
Yeah.
So this press can reach 25 gigapascal. It's 250,000 atmosphere pressure, and then 2,300 degrees Celsius. So this can simulate the conditions found down to the top of the Earth's lower mantle.
Yeah.
So near to the lower mantle.
Lower mantle.
Yeah.
That's not the very center, but that's below the upper mantle anyway.
Yes. Yeah.
Now you have something in there that says diamonds synthesized at
Yes.
50
Kilobar.
Yeah.
1,000 atmosphere pressure, 50,000 atmosphere pressure, and 1,500 degrees C. So we know that in most of the diamond that we found at the surface originated from the Earth's upper mantle, probably also part of the transition zone. So our press can cover the whole range that the diamond can be synthesized.
So actually, then, with this press, you probably thought about this before.
Yes.
You could make diamonds.
Yes, we can make a diamond, but the diamond wouldn't be very impressive because it's only millimeter size, 2 millimeter size. Yeah.
With a bigger press, you can make a bigger diamond?
If we can get money to purchase a 5,000 ton or 6,000 ton multi-anvil press, then we can synthesize probably half a centimeter diamond for using this press.
That's not bad. That's a terrific engagement ring, eh?
Yeah, half a centimeter is big. Yeah. And then you can even turn human hairs or ashes to diamond if you.
Oh, really? Anything with
Anything
carbon,
with
right?
carbon,
Has
yes.
to be carbon.
Yes.
A lump of coal. You know, have you tried to do that? I mean, to actually take a lump of coal and squeeze it down to a diamond?
No, I haven't tried that. But in our experiment, when we want to synthesize the iron carbide samples, we actually produce some diamond, because this is the byproduct of our experiment.
Yeah.
Actually, that is not what we want, because when your graphite sample chamber become diamond, it's very hard to polish, because
Yeah.
you need to use diamond powder
Yeah.
in order to polish your sample chamber. Yeah.
So, you know, you mentioned that there were diamonds at the upper crust.
Upper mantle.
Upper
Yeah.
mantle,
Yes.
sorry.
It's mainly.
Where is the crust anyway? Is that above or below the mantle?
The crust is above.
Above the mantle.
Yeah, it's above the
So
mantle.
if it penetrate the crust, go to the upper mantle,
Yes.
and you can find diamonds there.
Yes, that's really, it's a long way down, because it's very difficult to penetrate
It's not worth it.
even the crust.
This wouldn't be profitable, no.
No.
No, okay,
It's-
just checking. Just thinking about the business end of things.
Yeah.
Okay, and so now when you what I'm really missing, and I'd like you to explain it before our next break, is so you're trying to simulate the pressures that would be involved down below.
Yes.
That's why you say this is a trip to the center of the Earth where the pressure is so high and the temperature is so hot. But what does that teach you to take some element or compound or whatever and put that kind of pressure? What does that teach you? What do you learn from doing that?
So what we learn, so it's not only that we want to squeeze our samples to the conditions that are found in the interior of the Earth. So we want to probe the material properties that is under this condition, of the samples that is under these conditions.
You want to see how much, what happens to that material if you squash it, whether it splits or fractures or melts or whatever, right? Is that what it is?
Yeah, that's, we want to know all these material properties such as density, because and the sound velocities, and also the melting temperature of this substance under these pressure conditions, so that we can apply this, we can use the knowledge about these material properties, and then we can make a model about the Earth's mantle or the Earth's core.
So give me an example of how the data that you get about this material, whether it fractures or melts or what have you, how would you use that in material science or in some way, for the benefit of science or mankind or humankind? How does that help us to know the properties, the reactions of this material under pressure?
Yeah, there's so my research is mainly about it's basic science research. But you can also apply these high pressure techniques to do some material science research. For example, one of the professors in HIGP, so he has his name is Mercury Magnani. So he's working on this boron carbide. So these boron carbide materials, it is it has so it is used. It's quite hard, right? It can it is used in some as some armor materials for army. Like if you want to have these hard materials and then can sustain like a significant shock from a bullet or some other forces, and then so you can use these material properties that is found at high pressures.
Yeah, so that's so what would you call that? A compound, a special compound?
Yeah, boron carbide. Yeah.
That is.
It's very light.
Very light and very strong.
Very strong. Yeah.
And if you put pressure on it, you can make it very strong beyond that. And you can use it for things, material science. So very interesting. Let's take another break, actually, Ben. And we come back, I want to talk about the conference that you're going to, what they're going to do there, and how this science is evolving, how long you've been in it, what it looks like for you as a career, and what the world industry of this kind of compression science, if I can say, looks like and where it's going. Okay? Yeah. So that's Dr. Bin Chen of the Hawaii Institute of Geophysics and Planetology, the School of Ocean Earth Science at UH Manoa, here on Research in Manoa. We'll take a short break and you'll see, we'll be right back.
Aloha, I'm Kili'i Akina, president of the Grassroot Institute and host on Ehana Kako, a weekly program on the Think Tech Hawaii broadcast network. Ehana Kako means let's work together. Think of the sad alternative, let's not work together. Here in Hawaii, with all of our diversity and the richness of the people, it's important for us to come together around issues on the basis of what's right, what's good, and what's going to serve the common good. And that's what we try to do at Ehana Kako. Every week, we interview movers and shakers, people in government, business, and other sectors of society to talk about how to create together a better government, economy, a better world here in Hawaii that can bless the rest of the world. I thank you for your attention to Think Tech Hawaii, and we look forward to seeing you every Monday, 2 to 3 p.m. on the Think Tech Hawaii Broadcast Network. We're Ehana Kako, and we wish you well. Aloha.
Okay, we're back. We're live with Dr. Bin Chen of HIGP at SOWEST. We're talking about, finding out what's going on at the Earth's core. He is taking us on a mineral physics journey to the center of the Earth, the core. So you were talking about, some of the mysteries of the planets out there in the solar system, because they all have cores, as you showed in one of your early charts.
Yeah.
And you have unlocked mysteries. Tell us about that.
Yes, it's about Mercury. So Mercury is the innermost planet in our solar system. So it is the only planet other than the Earth has a global magnetic field. So we use our high pressure device, a multi-angle press, to simulate the conditions under found in the Mercury's core, and then we studied the melting relation of the iron-sulfur system under these conditions, and then we found a non-ideal behavior for the melting of the iron-sulfur. So the melting temperature of the iron-sulfur compound it decreased at a certain depth in the in the shallow depths of
Decreases.
the
That would be reversed, though. Usually
Yeah.
it increases as you get closer to the center. Now, why is it decreasing?
This is
A mystery.
it's still it's not a mystery, but we have some understanding that it's still not the result. So in our experiment, we found it's the melting temperature decreased for a certain composition of this iron-sulfur system. And that is due to the non-ideal melting behavior of the iron-sulfur.
So it's a characteristics of the material you're looking at.
Yes.
Some material will have a lower temperature as you get under a greater pressure.
One example is ice. When you squeeze ice
Yes.
at 0 degree, and then
Yes.
it will become water.
Yes.
That's the reason why we can skate on ice. Because you can squeeze it to become water, and so that it can lubricate your blade, and then you can squeeze it.
I used to skate a lot. So now you spoke in the break about carbon. What did you find out about carbon?
Carbon, that is, so we know that the Earth's core is not only made of iron nickel, because it should have some light element in the Earth's core. Because that is due to the reason that iron itself cannot explain the density and the sound velocity that is determined by seismic studies. So there should be some light elements such as carbon, oxygen, silicon, hydrogen, or sulfur. Yes.
Yeah.
That's one.
So you want to take these various materials and put them under various weights and test them and then make data on how they react to the testing. And then by doing this, you can logically infer what is happening at the center of the Earth or any planet.
So the most direct measurement is by seismic studies. So we can, seismologists have determined the density of the materials that is for the Earth's outer core and the inner core, and then the sound velocities of the materials for the Earth's
So you
core.
get kind of confirmation with what's coming up through a volcano or whatever.
There's probably not much material coming up from the core to the surface.
Okay.
Yeah. So what we are doing is we are trying to do a match. When we have a candidate material, we squeeze it to the core conditions, and then we probe the material properties, such as the density or sound velocities, and then we can compare it with what a seismic was observed or determined about these properties. So if we can have a very good match, and then there's a high possibility that this compound is existed in the Earth's core.
Ah, so then you have confirmation that way.
Yeah.
Make a comparison.
Yeah, I
You
have
slides.
a few
Let's look at the
slides.
slides.
For the first topic is about Mercury's snowing core.
Okay.
So as we discussed that it has, we found a non-ideal melting behavior for the iron sulfur system. So it has the temperature decrease at the shallow depths in the Mercury's core. So that has a consequence that the Mercury's core might be snowy iron because you have a decrease in the melting temperature. So if the sulfur content in Mercury's core is higher than 7% and then there's a scenario, it's called a double snow state. So you would have this iron crystallize at the columnar boundary and at the shallow depths in the Mercury's core. And if the sulfur content is less, then we can have this single state or Ganymede-like state. So Ganymede is a moon of Jupiter.
So what is snowing, though? Is it like snowflakes?
It's possibly like iron crystal, like some kind of crystal.
Mm-hmm.
We don't, for now, we don't know like how large is this crystal.
But it doesn't fall, or does it?
It will fall because it is denser than the liquid, so it will definitely fall. So this
So it snows through the liquid.
yeah. So in the next slide, I have this nature news about Mercury, about our study.
Mm-hmm.
So they highlighted our study with a very interesting title. It's called Forecast for the Heart of Mercury. And
It's like Journey to the Center of the Earth.
yeah, it's emphasized our discovery that the falling iron snow may drive the planet's magnetic field.
Uh-huh.
So that is there are some follow-up studies from people who do geodynamic modeling. So they can use our model to simulate the magnetic field that can be generated by this scenario, and then they can compare it with what is observed about the magnetic field
Right.
of Mercury by messenger mission from NASA, for example. Yeah.
So, and this way you can get a handle on what's happening there.
Yes.
And so you use multiple logical techniques to sort of triangulate on a conclusion. And then you write an article for the journal Nature.
So this is highlighted by the journal Nature. It's
Yeah.
published in Geophysical Research Letters.
Yeah. That's a very prestigious journal, yeah.
Yeah.
So where have you been publishing, and what have you been publishing about?
So I have been publishing mainly in geophysical journals, like Geophysical Research Letters, like Journal of Geophysical Research, and Proceedings of Natural Science, Academy of National Academy of Science. So this is
These articles you're writing are collaborative.
Yeah,
Who do you collaborate with?
We collaborate with a lot of people in beamline, so in national facilities such as Argonne National Lab. So because they have this gigantic machine that we can use, and then we take advantage of the high brilliance X-rays they can produce, and then so we collaborate with them a lot, and then we also collaborate with the planetary scientists. Like for example, this Mercury snowing core paper, we collaborate with planetary scientists, trying to understand.
Here and where else?
Not only here, but in Midwest, in the Case Western Reserve University.
I saw the name Villin, Villin, in one of those slides. Is that one of your collaborators?
No, that is not one of my collaborators. It's one of the like component about the
Okay, it's a scientific term. Yeah. And how did you get into this area? Are we finished with the slides? We have more. I want to cover them. Okay.
I have So this, as I talk about the light element in the Earth's core. So there are sulfur, silicon, oxygen, carbon, hydrogen are the top candidate for the light element in the Earth's core, because iron alone cannot explain particularly the density of the Earth's core, because it's too dense for the Earth's core.
Mystery.
Yeah, this is so. In order to test this, so we in one of our studies we tested the iron carbon compositional model for the Earth's core. So the next slide shows our research at Argonne National Lab. So we use the high brilliance X-rays produced by the synchrotron. And then we use a panoramic diamond envelope cell to squeeze our samples. And then we probe the vibrational properties of this iron carbide phase, Fe7C3, to core pressures. And we measured the first ever sound velocity, seismic sound velocity of this iron carbide to core pressures. As we can see that the Earth's inner core, actually, the shear wave velocity of the Earth's inner core is enormously low, because it's only close to about 3 kilometers per second. So that is enormously low. So
3 kilometers a second?
Yeah.
That's fast for me.
If you compare it with the sound velocity of iron, so it is 6 kilometers per second.
Right.
So iron alone cannot explain the sound velocity, the shear wave velocity of the Earth's inner core.
When you say velocity, you mean moving.
The seismic velocity, the shear wave, is the seismic rays. It will travel through the Earth's interior.
Yeah.
So there's two types of seismic waves. One is compression waves, and the other is a shear wave. So usually,
Like a wave in water.
Yes.
It's just,
Yeah.
okay, it's got a waveform and all that. Yeah.
Yeah. So, so in order to explain this, the enormously low shear wave velocity of the Earth's inner core, so we need to have a component that has enormously low shear wave velocity, and then we found it. So it is Fe7C3. So it has a very low shear wave velocity. About
This is your discovery.
Yeah, it's about 4 kilometers per second. If we consider the temperature effect, so we could be able to produce a match for the Earth's. Yeah. So that is published last 2 years ago. About the carbon in the Earth's inner core. And then there's some news release about our research. So this is highlighted by the Advanced Photon Source and the Michigan News. So this is, I worked at the University of Michigan for 2 years as a research scientist. And also it's highlighted by the Deep Carbon Observatory, so which is now very big missions about to understand the deep carbon in the Earth's interior.
So how long have you been involved in this area of science?
So I graduated with a Master of Science degree in geochemistry in 2004.
What school?
At the University of Science and Technology of China.
Where is that, in Beijing?
That is in Hefei, Anhui province. So I spent 7 years there, and then I studied geochemistry there. And then in 2004, so I applied for graduate schools in the United States, and I was admitted to the University of Illinois at Urbana-Champaign. And then I entered this high pressure.
That's when you started working on this.
And I fell in love with planetary cores.
Fell in love with high pressure, no pressure. So you have a big conference coming up in June. It's only a few weeks away.
Yes.
This is the compressed annual meeting, and compressed is, I was trying to work this out with you, and I didn't realize that compressed is actually an acronym.
Yes.
So tell us about this meeting in June.
Yeah, COMPRESS is a consortium for material property research for earth science. So this is a community-driven program that call together all the high-pressure mineral physicists to work on certain aspect of our research.
Your colleagues in science, yeah?
Yeah, so they are all my colleagues.
Yeah. And
in
where is
science.
the conference?
So this conference will be held in Albuquerque, New Mexico, in late June, and my student and myself will go there to present our research.
Ah, okay. It was the research you just described about carbon?
Yes, one is about carbon, because my student have made some measurement about the thermal equation state of iron carbide phase, and then she's going to present her research, and I'm going to present the viscosity measurement of this iron carbon liquid under high pressure.
Yeah. So, fair to say you're committed to this area of science.
Yes.
This is your career now. Yeah.
Yeah.
And where is it going? Do you find that there are great possibilities for the future?
Yeah, this is a very young field, so it's also a multidisciplinary field. So it calls together a lot of disciplines like solid state physics, material science, earth science, and some people who can do computation. So that's a very dynamic and vibrant field, and I love to do some good research in this field.
Yeah, unlocking the keys, yeah.
Yeah.
Well, thank you very much for coming down and talking to us, Bin Chen. Bin Chen is a PhD with the researcher with the Hawaii Institute of Geophysics and Planetology in SOWEST at UH Manoa, and been talking about the mineral physics journey to the center of the Earth. What a great title. And let me tell you, Albuquerque has great Mexican food, okay?
Yeah.
Check it out.
Yeah, sure, I will do that.
Thank you, Ben.
Thank you very much.
Aloha.